In our last video for this section, we'll work a complete example that involves computing the limit of a Riemann sum from start to finish. So the motivation for this example is to wonder what happens when we let the number of intervals n tend to infinity. We mentioned in the previous videos that we're probably going to get a better approximation if we have finer rectangles. So if we were to come up with an expression that involves n the number of rectangles, and then let n tend to infinity, which is what calculus students are good at, right? Computing limits, then we would get a better or a best approximation to the area under the curve. In fact, I'm going to reference Theorem 1 on page 264 that states that if f is a continuous function on an interval from a to b, the limit here is the limit as n tends to infinity of the Riemann sum using right-hand endpoints, or the limit as n tends to infinity of the Riemann sum using left-hand limits, or using midpoints, is it reaches a numerical limit. And so that's what we're going to do, is we're going to find what we're going to ultimately call the area under this curve. And I've started with an example that's a triangle, which you could easily divide up into geometric regions to double check our answer. And I'm going to leave that to you at the end of the video. You could carve this piece up into one long thin rectangle and find the area, and then the area of this triangle on top. So here's how a problem like this might be stated in the text. Find the area under the curve f of x equals 3x minus 2. Again, I chose a linear one so you can check it with geometry. On the interval from 1 to 6, using limit as n tends to infinity of a right-hand Riemann sum. And so what that means is we're going to be using representative rectangles that are determined, their height is determined by the right-hand endpoint. And we're going to let the number of rectangles remain variable. It's going to be represented by n, but I'm going to just draw myself some samples so that I have something to look at. And I'm using the right-hand endpoint. So here's a subinterval. I go to the right-hand endpoint. That's my height of my how I'm basing my height of my rectangle. I'll draw one more representative rectangle. Then I'll draw a little dot, 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 like continue in this fashion, and then the last one looks like this, and I'm just coincidentally drawing them of width 1. We're going to keep this completely variable. So now, to find the width of the subinterval, it looks like it's 1, but in general, remember we find delta x by taking the length of the interval and divided by the number of the rectangles that we're forming. We want that number to remain variable because we're going to take a limit. And so in this case, delta x is going to be 5 over n. Next, I want to write a Riemann sum that's going to capture the sum of the areas of all these rectangles. And so here's how I might do that. And then we'll do the algebra on another sheet. So I'm going to sum using the same as the book's terminology. I'm going to use my counters being j. Sometimes we use I, sometimes we use k, but I'm trying to be consistent with our book notation. I'm going to sum from the first rectangle to the capital nth rectangle the area of each of these triangles. Each one of them has width delta x, which I'm going to write, and you'll see why later. I'm going to write out to the right. That's my width. And then this is going to be the height of my rectangle. And remember that I get the height by running up to my curve and measuring. If this is f of x, if this is the graph of f, I'm going to run up to my curve and measure that height. So I'm going to evaluate the height of my rectangle by seeing what each right-hand endpoint is, and I want that to increase with my counter. So for the first one, 1 is a left-hand endpoint. So I know I need to move over my counter, or I need to move over my starting point, so I've got to start at 1, but that's not my first right-hand endpoint. My first right-hand endpoint is 1 plus the little bit delta x. But that's only my first right-hand endpoint. What if I needed my second right-hand endpoint when my counter is 2? I will move over 2 delta x's. So that's then I would put a 2 here. Or if I need my third right-hand endpoint, I move over 3 delta x's. So what I'm actually going to do is I'm going to start at 1 and move over j widths delta x to get that jth right-hand endpoint. First right-hand endpoint has j being 1. Second right-hand endpoint has j being 2, and so on. So there's my format for my Riemann sum. And f of this right-hand endpoint is how I'm going to find the height of that rectangle. Okay, so now let's plug in the details of this problem, and then we'll work the algebra on a separate page. So that would be just copying, cribbing from what I have right here. Sum as j goes from 1 to n. What is my function? My function f is the multiply it by 3 and subtract 2 function. So I'm going to multiply my input by 3. And then subtract 2. I'm going to give myself some braces to let me know, hey, that was my f of my input. And also, instead of writing in delta x, let's write 5 over n. That's what we found delta x to be in this problem. All right, but that's not everything. I've just done f of my input, and now I need delta x. Remember, delta x is 5 over n. I've gotten us a fresh sheet of paper with the reminders of the pieces that we were working with. Here's our function and here's our interval. And remember that we had put together this right Riemann sum. We're not using limits yet. I'm not carrying my limit symbol around because all I'm trying to do is get an expression for r sub n. That's all boiled down so that we can just limit as capital N tends to infinity. So now let me do some work here. Notice that this delta x does not depend on our counter j. It's just 5 over capital N, and capital N is fixed. We're not limiting yet. So I can float that constant out front. It's constant with respect to my counter. So I've got 5 over N times the summation as j goes from 1 to capital N. I'm going to distribute this 3. That gives me 3 plus, now distributing to the second term, that gives me 15j over n. Or maybe I should just write it as 15 over n times j. Right, so that's 15 over n times j. And then the 3 doesn't distribute to the 2, so that's just minus 2. All that's my summation term. And then remember the 5 over n, I floated out to the front of the summation because it does not depend on the counter. Now I'm going to use my linearity properties of sums. Look in the section for the linearity properties to break these up into pieces. Maybe I'll write one more step, just recopying. I've got 5 over n. 3 minus 2 is just 1, plus 15 over n j. So now I've got 5 over n out front of this whole sum and 2 different terms. By using my linearity properties, the sum of a sum, I can break those 2 apart, and I get 5 over n is equal to, or let's see, sorry, previous line is equal to the next line. Summation as j goes from 1 to n of just 1, as well as the summation as j goes from 1 to n of 15 over n times j. Again, using a linearity property, which we technically used up here as well, I can float this term out front because it does not depend on the counter j, giving me, let's see if I can move this up a bit, giving me 5 over n, just recopying, sum as j goes from 1 to n of 1, plus 15 over n, sum as j goes from 1 to n of j. All right, and so now we need to evaluate what these two terms are, these 2 summations are. And I'll be using the power sums portion of your text to figure out what this summation is. But this one we can just kind of reason out. We're counting as j goes from 1 to capital N a 1. So that's a sum of n ones. So that's just n. It's like doing 1 plus 1 plus 1 n times. So this whole thing just evaluates to n. And I'm going to copy the 15 over n, and now I want to figure out what this summation is, and that's where I'm using the power sums, which are on page 265 in your text. The sum as j goes from 1 to capital N of the counter j would be, if you wrote it out, 1 plus 2 plus all the way up to stop at capital N. And some of you may recognize that as the Gauss's sum. This is, and I'm just pulling this straight from the power sums, n times n plus 1 over 2. Check page 265 for where I got that. That is our expression that we want to limit as n tends to infinity. Maybe we can do a little bit more algebra, and we can distribute this 5 over n. If I distribute the 5 over n to the first term, the n's cancel, and I just get 5. Distribute the 5 over n to the second term, this factor of n and this factor of n cancel. 5 times 15 is 75 over the 2. Remember that. Remember that these two factors of n cancel, and I'm left with n plus 1 up top and n plus 1 down bottom, or sorry, just plain n down bottom. And so that's the term that I'm limiting as n goes to infinity. That's our last step. Now, let n go to infinity. We're looking at limit as capital N goes to infinity of this expression. Which is equal to limit as n goes to infinity of just 5 plus limit as capital N goes to infinity of 75 over 2 times n plus 1 over n. And this guy is just 5. This limit, you can use L'Hopital's rule, or you can just recognize I've got linear over linear, and the lead coefficients are 1. That tends to 1. So this second limit is 75 over 2. And summing that up, I think I get 42.5. Because I believe this is 37.5 and 5 is 42.5. Now you check it. You compute the area geometrically. Just to see if we were right. We are.